in a bit of a time crush, but let's see what I can do. So this is around 1000. I haven't done any of the problems, or apparently I haven't even seen any of the problems from this round, so it should be interesting. Okay, Bismillahirrahmanirrahim, and let's begin. Are we gonna need that? Minimal coprime, subsequence update, remove exactly 2. Okay, a segment is coprime if L and R coprime. It's called minimal if it does not contain any coprime segment not equal to itself. If it does not, okay, so if you can't make it any smaller to understand a statement. Okay, wait. Segment is called coprime if L and R are coprime, so it doesn't care about the numbers in between. Given L and R, a segment of positive integers, find the minimum number of coprime. Find the number of minimal coprime segments contained in LR. Okay. So wouldn't this... Okay, this is kind of interesting. So you have 1 and 2, so that's just 1 is 1 to 10. So then you have because they did not explain the second one. 1 to 10, it has 9. 49 to 49 is 0. It reminds me of the overall. This reminds me of the Euler torsion function, but kind of interesting. What is, so let me just take out a calculator. What is 44,353 minus 9982? So it's 34,371. Why is this? Oh, yeah. Okay. Print R minus L. Well, the reason being that any input of consecutive numbers is always going to be coprime, and so anything larger than that will always contain that. So use this because it needs to be non-zero, and I think so. Let me just do one more. Okay. So 347, 351. This says 0. This should not say 0. This should say 1. 1. Because 1 to 1 is coprime. Okay, so 1 is a special case. I see. So this is the only special case to handle. If LL equals 1. Okay, so what if I do ans equals to R minus L? If L equals to 1, then max of 1 comma ans, because what I understand is, okay, so 1 comma 1 becomes a thing. I think this is how you would solve it. Let me just run this again. Probably should have better ways of running test cases. 49, 49, 0, 69, 420, 51, 1 and 1. Blah, blah, blah. Okay, cool. Now I'm going to have to navigate to the folder, which I would have preferred to have done earlier. But I think this should be it. Let's move on to problem B. Subsequence update. You're given an integer. Yeah, okay, nice. That was cool. You're given an integer sequence and a segment LR. You must perform the following operation as sequence exactly once. Choose a subsequence of the sequence A and reverse it. Note that this subsequence does not have to be continuous. So given a sequence and a segment, so that this contest seems to revolve around segments. Choose any subsequence of A, reverse it. Note that the subsequence does not have to be contiguous because, okay, it's a subsequence. Formally choose any number of indices, then change the ith element to the original value of the ik minus x plus 1th element. Okay, makes sense. Find the minimum value of, find the minimum value of a range after performing the operation. Okay. I can only do this once. That's okay, that's good. I mean, sometimes I would say that that's bad. If I could do it infinitely many times, then there's strategies for that. If I just do it once, okay. So we're trying. So there's going to be numbers So, well, I don't want to, I want to see the problem as well, so it's kind of the struggle. Maybe I can drag this over here so I can draw and think about it. So like if I have an array and then I have the segment from L to R, so this is my array is from here to here, this is my segment that I'm trying to minimize. It's going to have some numbers in here, and what I can do is when I'm doing this operation, if I don't select any numbers inside of this, then that's useless, so I need to select some numbers inside of this, and then so these elements are either going to be swapped with these ones if I take this and like reverse it like this, or they can be swapped with these ones. So I just need to compare elements over here and elements over here in a sense. What is the exact comparison that we're trying to make? So what would be the thing? So this has some elements already, and why would I, so why, and picking everything, so picking, yeah, so is it ever helpful for the subsequence to like span across this? I mean, obviously it's a subsequence, so it doesn't have every element, but would it ever make sense to take this, and then some elements over here? So what that would do, if I, where's the array? Okay, I guess I can't access eraser in low screen. But if you were to reverse it, then the elements over here go here, the elements over here stay here, and the elements over here go here. So it seems like either, and so the elements that came into the middle were only elements from here. So it seems like there's no point in having it span everything, because then if I have elements here and elements here, only these ones can swap with these ones. So this swaps with that, this swaps with that, this swaps with that. So I guess it is technically possible. This swaps with that, this swaps with that, this swaps with this swaps with this, right? Because of how reversal works. No, wait, sorry. No, that's not how reversal works. If I have this, and this is going to swap with this, 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 which means if I have a section here and a section here, and my range L to R is like this, then nothing meaningful happens, because the elements that are swapped are the ones which are inside. If it's like this, then it only takes an element from this section. If it's like this, so it seems like having it span across doesn't make sense, so either from the left or from the right. Now how do we do this greedily? Okay, 3 2 3 1 2 3 3 1 3 3 1 2. What are these inputs? And L and R, another array. Okay, so this is the segment and then the array. Essentially I'm picking elements from outside my segment and I'm putting them in my segment. The thing that's coming to my mind is a binary search, but I don't think that's a good idea. I mean, like L and R, I could try to create some minimum value. So everything from the left, take left, swap it here, right. This is an interesting problem. Shouldn't be hard, but missing the last observation. So if we look at this example, we're trying to minimize from 1 to 3, so I can only select from the right hand side. The only number which would reduce over here, well, 4 would reduce 6, and 3 would reduce 6, and 2 would reduce 3. So you would take all, and then output is supposed to be the minimum value. So yeah, which is, wait, what? Why is this 8 and not 9? So they're only swapping 6 and 6 with 3 and 2. Interesting. So they're only picking values which are smaller than the minimum in my segment. Why? Was that always the better idea? So like, let's say I had 3, 6, 6, and I just had like a 4, right? It still would be meaningful for me to swap the 4 and the 6. So there's some sort of ordering going on here. So, okay, so my conjecture is consider the sorted order of this, consider the sorted order of this, and then swap this with this, swap or no, okay, so swap the smallest and this with the largest and then swap this to this. I guess that would be the strategy, because that would be greedy and seems about right. So then in that case, let's get to writing that up. So input format for underscore in range int input nlr equals map int input dot split a equals list map int input dot split, and then range. So I can break this into 3 things, right? So left equals to a up till l, right equals, okay, I need to check the indexing. This is 1 based indexing, so that should work for me. So if I say the limit is 1, so if I'm starting from 1, so this should be l minus 1, yeah, l minus 1 till I think r, because that's inclusive but it's 1 based, so that's mid, and then right is from r onwards. So I'll also print that just to check that I'm doing this right. Let's try the last test case because I spent most of my time on it. Yeah, that's splitting it exactly how I want to do that. Then I do left dot sort, right dot sort, mid dot sort, and then I just need to figure out whether I want to swap with the left, with the right. I'm also going to have to maintain the scores. So let cur equals to sum of, or mid sum equals to sum of mid, and then I try once with left and I try once with right, left, right. For I in the range len of left, so I create a left sum which equals to mid sum originally, and then I go through each element in left. Particularly I swap the smallest with the largest. What was the strategy? It was smallest with the largest, yeah. Okay, so go with the smallest element. Left sum, if left I is less than mid negative I minus 1, also I need to check I is less than length of mid. Okay, so if this is the case, then left sum minus equals the difference between the two values. So left I, okay, and I just keep doing that, and that what, well, this is sorted. Since it's sorted, can it happen that this doesn't hold but then it later on holds? So I know mid minus I minus 1 is going to be a smaller value, left I, well no, I know whatever I take for left I is going to be a larger value. Whatever I take, so like as I'm going through this list, the values are getting larger, the values are getting smaller, so there will just be 1 point. So this will be a break point. Okay, do the same here. Right sum equals to mid sum for I in range len of right. If I is less than blah blah blah. Okay, and right sum and right. There's probably VS Code shortcuts to do this better, but it's fine. print min of left sum, oops, left sum, right sum, mid sum. I think mid sum would already be covered, but better safe than sorry. 6 2 1 1 2 1 is 1, 3 2 3 1 2 3 3 3 1 3 3 1 2 is 6. Let's try. Okay, let's just go through all the cases. 4 2 3 1 2 2 2 is 3, and 5 2 5, and 3 3 2 3 5 is 11, and 3 6 6 4 6 1 3. That's not what I wanted to do. 6 1 3 and 3 6 6 4 3 2 is 8. Great, so that seems to be working the way I need it to. So let's submit that. Is it good to submit with like such a rough idea? I'm pretty confident in the idea, which is why I'm submitting. If I was doubtful, I wouldn't. There we go. Remove exactly to. You're given a tree of n vertices for performs for an operation exactly twice, like this is short description. Select a vertex v, remove all your edges incident to v and also d vertex v. Okay, so given a tree of n vertices, select a vertex, remove all edges incident to that vertex from the tree. So this would separate the tree above and the tree below. So this would create like a bunch of new trees. Please find a maximum number of connected components after performing the operation exactly twice. Maximum number of connected components after performing the operation exactly twice. Two vertices x and y are in the same connected component if and only if there exists a path from x to y. For clarity, note that the graph with 0 vertices has 0 connected components by definition. Okay, sure. N is going to be at least 2, so this part is useless. Okay, so you have a tree. So like the easy thing that comes to mind is, okay, just take the one which has the highest degree and then cut that first, right? So like take the one with the highest degree and cut that first. I will say I do think I've seen this problem a bit before, but I haven't fully solved it before. But yeah, so you cut these, and then that will create new component, new component, new component, new component, and new component. Well, this is one big component. And then after that, I want to select the one with the highest degree again. Is that justified, or would it ever make sense that I actually select two nodes with lower degrees? So if a node has a so let's say if this node has a degree strictly less than another node, I also know that the degree of a node, so after this cutting, the degree of these nodes will reduce by at most 1. So if I were to cut something which had a less degree than this, and then for my second cut I cut another thing, and if I'm saying it gives me more, well, I know the degree of that other node so if it doesn't neighbor the target node, then it would have just made sense to cut this first and cut the second, so it doesn't matter. So it only matters if the resulting thing neighbors something, right? Like if the largest degree node doesn't neighbor, so in the optimal, let's say there's two nodes I have to cut, and if one of them has the largest degree and it's not wait, I don't know what I'm trying to say. I guess I cut this, and then this will reduce the degrees of other things by at most 1. I also know that the number of components will be the degree of first cut plus degree of second cut. But the only thing is that depending on what I cut first, the thing I cut second can have its degree reduced by at most 1. So the only case, so I would never consider anything which is less than this. That wouldn't be useless. That wouldn't be useful. roughly speaking, with like some amount of symmetry. Cutting anything with a lower degree would not be helpful. If something has a degree like 1 less than this, then this would have to have a degree of blah. Okay, so this is m and this is n. Like so if the max is m and the max here is n in that case, then another combination which goes for anything less than m, so it goes for something which is m minus 1, then needs to make a second cut of n plus 1. But I know that this cannot be m, because this cannot be the same node which was associated with m, because if this combination works, then it would have just worked if I did m first. So it needs to be something which is not m, or it's not the thing I identified as m. So it's n plus 1, but it's not m, so the second, this n plus 1, n, yeah, like if it's not this node, it's some other node, and I know some other node in this case has a degree of n, and so in the best case it could have had a degree of n plus 1. So this would be at most as good as doing this. The only thing that's left to consider is, okay, there might be multiple options for the first cut, right? There might be multiple nodes with the same degree. I don't know if I drew that equally. It's just that if I cut all of this, and then this has a child with a degree of 4, and this has a child with a degree of 4, then for my second cut I want to consider this child. Well, another thing is, why would you not just go for this directly, right? Okay. But the rough idea is I want there to be a distance between the nodes I cut. Okay. So I can order by degree, I can cut the largest, and then I can evaluate again. Or, sorry, one more useful example is, there's two nodes with the same degree m, and then there's one node and there's a node with degree n. So if I cut this, then this becomes n minus 1, but if I cut this, then this stays n. So it would have been helpful for me to have cut this, but if I think of it like this, it would have also just been more helpful for me to cut this and this, except in the case maybe that you have this has 4 and this has a degree of 4, and then this has a degree of 4, and so now I have to choose between, do I cut this, do I cut this, do I cut this, and so it would have been more helpful for me to cut this and then this, like as in cut this and then this, as opposed to cutting this and any of the others. Okay. What does this mean though? Right, like basically the things I cut, I don't want there to be a parent-child relationship, like I want to avoid that. So what if I go for the lowest node which has a given degree? So if I go for the lowest node and I cut that and all of its neighbors, does that solve everything? So we cut the lowest node with the highest degree, and then I cut anything else. So let's say there were multiple nodes with super high degrees, except one pair was a parent and child, and then there was some pair that I could cut which was not parent and child. That means that they're either, yeah, so if it's not parent and child, something exists which is not parent and child. If I feel like if I just cut the lowest one and then check the rest of the graph, that should work. So the idea that's coming to mind is take a tree BFS to get the levels, and then cut the one with the highest degree at the lowest level, and cut the one with the highest degree at any other level except for my parent, like try not to cut off my immediate parent. And the reason this works is if there's anything at the same level, then that's not a problem. I can cut that out. If there's just my parent, so like if there exists some pair which is not parent and child, so either I'm part of that pair or I'm part of that pair, right? Because like as a child I'm only part of one parent-child relationship, and if there exists a non-parent-child relationship, then you could swap out one of the nodes in that non-parent-child relationship with me, because at best it could have had my own parent, but if you put me in, okay, I think this is a good idea and this should work. It's just going to be a bit difficult to write it up. For underscore range int input n equals to int input, and then n-1 contains the edges. Okay, so graph becomes and the values are from 1 till n, so I is for I in the range 1 comma n plus 1, and for I in the range n minus 1, u comma v equals to map int input dot split. Okay, and then u dot sorry graph of u dot append v and graph of v dot append u, and then I do BFS. So, and I can just start BFS from, I don't know, node 1. I'm gonna import deck from collections, import deck. Or firstly, I also want to figure out what's the largest degree. Another way I could do is I can find a node which has the largest degree, and I can sort of go through its neighbors while they have a largest degree. What I can do is I can take that as a root of a tree, or not a root, as a leaf. Well, it's not a leaf of a tree, it has no two edges. But there must be a way to do this. Could, instead of like doing BFS from some point, could I just take the node and make that a leaf, or as close to a leaf as possible. So if I have only one neighbor, then it's fine. There, basically, I don't want to have two neighbors which have that. What is the maximum number? Well, if this can be simplified, yeah. So if there's even 3 nodes with that max degree, then I know one of these are not going to be parent-child, so I can just easily output the answer for that. And if there's only 2 nodes with the max degree, then just cut those 2. So degree equals to a list of len of graph, or yeah, graph of I for I in range 1 comma n plus 1, and then degree dot sort reverse equals true, but then I'd lose that sure, fine, max becomes 2 degree because 0, right? And then for I in range n minus 1, count becomes degree dot count max. So this will tell me how many. If count is greater than 2, print So the cut adds number of degree, number of trees. So if you have 1, 2, 3, 4, and you cut, so this becomes a tree, this becomes separate. So everything I cut off becomes a separate tree, but there was already a tree that, so the trees increase by a value of degree minus 1. Okay, got it. So print max, so 2 times max minus 1. And if count equals 2, then I have to do something else. Print degree 0 plus degree 1. So if the count is 2, then I just have to check, am I neighbors? So for I in range n minus 1, if len of graph I, sorry, so this is from 1 to n plus 1, my bad, did I do it right here? Yeah. If len of graph equals max, then I check for v in graph of I. If len of graph of v equals max, then that means I neighbor that thing that I don't want to do. Then print degree 0, or print 2 times max minus 2, else no. So note that if n is 2, so this I need to keep track of. If n equals 2, then print 0, number of components. They define this as your components. Okay, continue. Print 2 times max minus 2 and break, else print 2 times max minus 1. Hopefully that will work. 3, 2, 1, 2 gives me 0, 4, 1, 2, 2, 3, 2, 4 gives me 4, which it shouldn't. 1, 2, 2, 3, 3, 2, 4. So there is a node which has a degree of 3. So it adds 2, and every other node because I have to note that the degree of my friends reduces. Shoot. Well, okay. What if I don't sort it, but I just take this as max of degree? Count equals to degree dot count max. It's fine. If there's only one of these, then degree dot pop. Well, okay, then I reduce the degrees for, okay, max node equals to degree dot find your degree dot index of max, and for v in graph of max node plus 1, degree of v minus equals 1, and then at the end I pop max underscore node and then print degree of 0 plus degree of 1. Okay, I had to leave before for quite a while, but I'm back now. Unfortunately, the virtual contest is over, but we can still solve the problems. Okay, so I was debugging was so this is fine, this is not an issue. It's just that, okay, if count equals 2, then what I should ideally actually do mm, mm, is, so if count is 2, then do something. If so in any case, okay, I think I got it. So if count is greater than 2, then do this. That's fine. Else, in any case, what I do is answer equals currently it becomes 1, then answer plus equals to max, then for v in graph of degree dot index of max plus 1. So for each node, so each neighbor of the node with the max degree loses its degree by 1. Okay, can it happen that 2 of them have the max degree, but it would have been better, and they're neighboring, and it would have been better. Well, okay, if they aren't neighboring, then I can do both, and if they are neighboring, then would it have ever been better for me to have done this and something else as opposed to doing this and this? No, I don't think so. So for v in graph, so I just reduced the degree of everything else. So this increases more, okay. And then ans plus equals to max, and then okay, yeah, that node has to get popped. So degree dot pop degree dot index of which has that max value still. Well, and then ans plus equals to max of degree minus 1, and then print answer. Hopefully that should work now for the other cases. So 3 2 1 2 0, then 4 1 2 2 3 2 4. Trace back answer. Did you mean answer is not defined? Okay, that's fine because I forgot to do that. 4 1 2 2 3 3 4 is 2, and then this case that is 4 logically. So if there's more than 2, then there exists some pair that I can take such that I can take the max both times. Otherwise I take the max, I subtract, or I reduce my neighbors, and I take whatever else is the next best option. Alright, seems logical to me. If my nodes are 2, then I will run out of things, and in every other case, if my nodes are 3, what happens if I, so what happens if I have 3 nodes, 1 2 2 3, right? And I get left with 1 because yeah, I'm going to remove 2 of the nodes, so I'll only be left with 1 node, so fine. Okay, not p1, p3 dot by, and submit, and I can load up. Oh, that's nice. It's at 23 test cases. Yeah, nice. Okay, problem D. Dijon, blah blah. N plus m. Why is there a GIF? Wow, this is fancy. N plus m distinct points. So there's 2. It seems like, yeah. So there's points on the lower line, points on the upper line. Initially the score is 0. To increase the score, I have to perform operations. Choose 3 points which are not collinear. So 2 from the lower line, 1 from the higher line, or vice versa. Increase your score by the area of the triangle formed by these 3 points. Then erase the 3 points from the plane. Okay. I really appreciate the visualization. It's very cool. Let k max be the maximum number of operations that can be performed. For example, if it is possible to perform any operation k max, if it is possible to perform any operation, k max is 0. K max being the maximum number of operations to perform. For example, okay. Define f of k as the maximum possible score achievable by performing the operation exactly k times. Here f of k is defined for all integers k. Okay. And then if k max and the values of so okay, yeah, this is I guess the tricky part, which is find the most you can do for each number of moves. And how many points can you have? You're gonna have 10 to the 5, 10 to the 5. It's going to be an interesting problem, but it's kind of why I wanted to do the div2d problem. Okay, so let's play around with this. Get my writing pad out here. I think I'm gonna have to actually draw properly now. So I have some points on an upper line and some points on a lower line. And each time I'm getting the area of a triangle, but keep in mind the height is constant no matter what, so this is just really I'm trying to consider the base of a triangle. And the number of triangles as well. So half into base times height plus half into base times height common to base. So I'm just trying to maximize the sum of the bases, right? I mean each base is going to be multiplied by oh, that's why the height is 2. Okay, so it's literally just sum of bases. Now the only issue is I need a point above and I need like points below. So the maximum number of operations I do is I take from the larger set until the sets are equal, and then I take 2 from here, 1 from here, 2 from here, 1 from here, right? So like while there is something larger, take 2 from that and take 1 from the other one. Just keep alternating if they're equal at any point. Sure, that makes sense. So that's how you get the most number of operations. Okay, sick. But now, what does it mean to maximize? So if I want to maximize, ideally I want to take the points which are the most outwards as possible, right? Because if I take the points which are as far out as possible, I'm getting the most amount of base in one move, which is cool. So I get the most amount of base in one move, then the most amount of base in one move. As opposed, so like one idea is you do this and this and this, whatever. The other idea is you do this and this and or like something like that. But clearly the one which is trying to go from end to end is better, and I think logically it's probably the best to go like about this greedy. So there's a mix of greediness in the problem. The only issue is okay, and when I pair these, I should pair them with like a central element here, so that this distance is still as large as possible. And so while I'd want to sort of do this greedily. Oh, but no. Yeah, so while I'd want to do it greedily, that I compare what's the largest here, what's the largest here, and if this is larger, do this, and then consider what's the largest here and what's the largest here, and it's still largest to do this, and what's largest here and what's largest here, and if this is largest, do this. So that's cool. That works for sort of being greedy. The only issue is that this isn't keeping in account the number of points that there are. So this risks running into a limit, because it might take from the line which has fewer points, like a line which has fewer points but they're just spaced further apart. You'd exhaust them. Ha ha ha. Is there anything in the constraints which can help? So 10 to the 4 test cases, 2 times 5 numbers. Value goes from negative 10 to 9 to positive 10 to 9. Okay. It's easy to figure out what K max is. What is interesting is that I mean, okay, it doesn't seem too hard. There's something in my mind. See if I can figure out how to express it. So, like you have in basically when you're trying to find the max, that will tell you how many upper and how many lower pairs you can take. So for example, if you have 3, now the only thing is if you have 3 and 3, well no, then yeah, you'd get 2 and 2. Well, sorry, yeah, that's the exact problem, that you can end up with some choice. So if you have 3 and 3, you can either do 2 of these and 1 of these, or you can do 1 of these and 2 of these. Sorry, I'm doing it wrong. In this case, it's just 1 and 1. So if you ever have equal, if you have equal number above and below, then it's 1 and 1. If you have 1 extra below, ideally, so okay, keep in mind if you had just 2 and 2, now you can either do 1 above or 1 below. So now this is not like a AND case. Okay, so 2 and 2 is going to be the interesting scenario. 2 and 1 is easy. Obviously anything with 0 is easy. 2 and 2 is the problematic one, it seems. What about 2 and 3? Oh, with 2 and 3, if you take, yeah, you can't really do much even with 2 and 3, because if you take from the bottom, then this gets exhausted. If you take from up here, then, well, that's, yeah, sorry, that is the better thing to do. No, wait, yeah, even if you take from up here, you exhaust this, you don't. This 2 and 3 is fine. 4 and 2, so this should just have a fixed amount of triangles I can do, which is boom and boom, and that's always going to be the smart thing to do, as opposed to doing this, which is only 1. But while there is a limit, there's not there's some things I can do intermediately which would not make sense for the maximum. So like for the maximum number of triangles, it wouldn't have made sense to take this one, but if I just want 1, then it works. So quite trivially, like one thing is you get your list of points, you sort them, you give a list of this and a list of lower points, and you sort them. So you can have a left pointer and a right pointer. maybe try like thinking a binary search way. What if I knew how many lower and how many upper I'm going for? And so what I would do is I do all the lower first, and then I do all the upper for upper next. Does it matter if I do all the lower first or all the upper? No, yeah, that would sort of matter because the logic was to go greedy, but no, it shouldn't matter, right? Like, and if you're always taking the central upper points, because like once I've fixed the upper, I've sort of said to myself that I'm not going to use these points and these points, and I'll always be taking from the middle. Similar, so yeah, so the order doesn't matter. Once I know lower and upper, I can tell how many I can do with that combination of lower and upper. The problem is, how do I figure out how many lower and upper I should go with? Can I binary search? So for a given sum of lower plus upper, one thing I have is my K-max allows some things. Well, can I not think of this as like a DP problem? So like, what's the score I can get from upper if I take I, and what's the score I can get from lower if I take I? And these are lists that I can sort of pre-compute, and that's fine. And then when I want to do the score for different values of k, the problem is there are, so like this is n values and this is n values, so combining these two, there's n square, but there might be some way to optimize this. So score of k becomes, I believe it's like max ij such that score or lower of I plus score upper j, right, and where such that I plus j equals to k, right? So this is fine. I know that both of these lists are increasing lists. It's just that it's not like linear. It's like a jagged increase. Well, that's too jagged, but it's like a jagged increasing matrix. Like lists, both of the lists are increasing. Is there like some sort of intelligent idea I can apply here that if you've tried something, there's no point in trying something less optimal? So perhaps for that I can consider my greedy technique, which is like, okay, my greedy technique tells me I would want to do this many uppers and this many lowers, and that So my greedy would tell me that for k how many I would want to do, but the problem is this doesn't. So this would tell me up to a certain k what's the best I can do. From then on, the greedy strategy would tell me what's the best up to a certain value of k, but from then on it's kind of useless. Because it doesn't care about exhausting the points. It might just exhaust the points early. Okay. Once the points are exhausted, then can I start using the array? So now, let's say the points have been exhausted, and then so like up till k I was doing L is like 5 L, and upper I was doing 3 of them, and now I'm trying to do for k equals 9. So, and the thing that I ran out of, maybe that's also important to know, right? So let's say I ran out of lowers, right? So I ran out of L. Then I know that I take L to be 4 and U to be 4. Is that guaranteed? Or so U to be 5. Is that guaranteed? Well, firstly, I know I have to reduce this before I can increase upper. But is this guaranteed to be the best? Or is there a case where I do L equals to 3 and U equals to... well, I guess the benefit that I have is not only are these lists increasing, but they're always increasing with lower and lower gradients, because I always take the first actions first, which means this should be solvable greedily, that I want to increase this as less as possible. So I do this, L equals 4, U equals 5. Then for k equals 10, I do L equals 3, U equals to 6, L equals to 2, U equals to, well, not 7, sorry. Not 6, but 7. And here this would be 9, right? Yeah, so this would be for 10, for 9, for 10, for 11. Okay, so the logic seems to make some sense, but we need to try run this on some of the stuff which we have. And this is going to be painful to draw on my laptop, so I'm just going to like draw it up on paper and tally it for myself. Fortunately, I cannot really show that. Okay. So which data should I consider? This one sounds nice. So if we sort this, there's a point at 1, there's a point at 20, 27, 42, 43, and 100. And you have 100, 84, 184, no wait, sorry. In descending order 1, 22, 24, 77, 84, and 100. And so if I was going about it for the max, I'd take from the top and I would pair it with maybe any of the central elements, let's say pair it with 24, and take from the bottom, pair it with any of the central elements, let's say 27, then take from 43 minus 20 versus 84 minus 22. So 84 minus 22 is better. Now I have to eliminate 42, and then 20 and 43 is my only option left. I take 77, right. So the sums I'm getting 99 plus 99 plus 62 plus 23. So for k equals 4, it should be let me write this out. This is 198 plus 85, which is 283. So that is good. Now let me create that upper and lower list. So if upper is 1 is 99, then for 2 the next best you do is 20 and 43, which is 63, which would give you, so 99 plus 63 is 154. Sorry, 99 plus 63, 102, 162, and then 27 and 42 is 15. And then for lower you have 99, you have 62, right? Yeah, 62, and then you have 77 minus 24, which is 53. Nice. And so before, so you're doing 283 by taking 162. Oh, I was not adding this. So let me add this. So lower 99 plus 62. Huh, 62. There's something really wrong here. 99 plus, wait, have I done this the other way around? No, I've just done 99 and then 43 and 20, right? So it's 23 is added, so this becomes 122, and after that you add 15, so that becomes 137. For lower you have 99, then you have 62 is added, which puts you at 161, and then you add in 53, which puts you at 214, right? And now the current optimal state that you start with is from your upper you were taking 2, and from your lower you were taking 2, right? This was giving you 283. Now, and you ran out of upper, well, you ran out of both actually. Okay, well, the way you reduce it, you'd move either this pointer or this, you'd either move the upper pointer left or lower pointer left, so whichever one decreases by least, so you move the upper pointer left, so this will be 161 minus 90, 161 plus 99 is well, 170 plus 90, 260, and then you have to move another one to the left, so you move this one to the left. Okay, 198, and then 99, and then 0. Yeah, so that does work, but I am skeptical. So the idea is if I move this left, it actually frees up 2 of these points. So what if greedy choice, okay, it kind of worked. This frees up 2 of those. Well, so with reducing this is fine, and in fact with reducing no, I don't think this is cool. Well, oh yeah, the point is still that the jump is reducing, which is why the gradient is always decreasing. Oh wait, that works against me. Oh wait, right. Well, yeah. Well, moving forward, that's easy. It's actually but less than k is easy. It's more than k, which is what this is supposed to be handy for. And if you're going for more than k, the fact that the gradient is decreasing should be handy, because you always go for the one which is larger, because you know the one which is smaller in the future, it's also going to be smaller. Yeah, that okay, checks out. So let me try it for this case. That's a nightmare with the numbers. What about this case? So if you were to do it greedily, yeah, that would not be a good case. I think this is the only case I can really do. Unfortunately, the numbers are very annoying, but can't do much about it. Maybe I could, at the very least, get Python to sort this for me. Python 3 x equals to x equals to input dot split and then sort x, and then say x dot sort, and then x. So okay, this should help a little. Still a mess, but negative 207. This is too difficult to do. Let me try just creating my own example. So case where I run out, so let's do negative 100, 0, 100, 200, and the lower half you have just 2, which is negative 500 to 500. And so with one move, this is the best thing you can do. However, now you create the list for upper and lower. So this is the upper's first element is 300, next element is 100. Lower's first element is 1000, it only has one element. K for up till 1 is fine. Then for k equals 1, I stop here. For k equals to 2, I need to move the lower wala arrow left, and I need to move upper forward by 1. That's 300. For k equals 2, I need to move upper forward by 2. So yeah, k equals to 2. This is 100. Well, not so it's 300 plus 100, which is 400. Which I think logically it does make sense. I think this is overall the idea. So let's write this up. Could be wrong. That would be fun, but hopefully not. For underscore in range int input. I realize I should just join the Google Meet from my tablet, but it is what it is. I at least explained the logic before, so that should be fine. Okay. So what does the input come in? N comma m equals this equals map int input dot split. And then a equals to list map int input dot split. Similarly for b, and then I sort the 2, b dot sort. So I need to first, so let's just create a upper list equals this and lower list equals this, and let's just populate this. I'm just assuming a is upper, right? I mean, it doesn't really matter. Y equals 0. It is like completely arbitrary, but yeah. For I in range n by 2, so n is the number of lower points, yeah. I in range n by 2. Let me initialize upper list with 0. Upper list plus equals to this is sorted in ascending order. Let me sort it in descending order. That will make it slightly easier for some reason. AI minus negative I minus 1. So this should be fine. Take the previous element, you take the extreme elements, you take the difference. This is fine. And I wish my multi-cursor does not work, unfortunately. Lower list, and then BI and BI and M by 2. So this will produce the list. That's good. Now keep track of rem upper equals n, rem lower equals m. Ans becomes a list which currently has nothing, or yeah, so there's cur equals 0 and there's ans becomes a list, while rem upper and rem lower, so while neither of them are non-empty, or neither of them are empty, and their sum is greater than 2, so I can still form triangles, then figure out the best I can form. So lower best becomes basically so if I have lower or a wait just completely just inverted everything in my brain. Wonderful. Okay, let me actually use the convention that they use. Right, so let's do upper using list A, sorry, lower using list A, and upper using list B, so that it's easier for me to manage. The remaining of lower upper is M, right? Lower is N, upper is M. Okay, it's maybe a good idea to stick to the notations they use. Okay, lower best becomes, so also if two are the same, then I should opt for, well, if two are the same, it shouldn't matter what I opt for, I believe. But I think for, yeah, so I will not, I'll just keep my code simple, because I think that, I mean, ideally you don't want to pick the one which has more points, but I don't think it'll matter that much. So lower best, if I've used up, so there's the points which I've used up, but there's also the lower left equals 0, lower or upper left equals to 0. So lower best becomes lower left minus a of negative lower left minus 1. Similarly for upper, B upper, B upper. It's a fun problem. Okay, if lower best greater than upper best, then I take the lower one, which means cur plus equals to lower best, lower left plus equals 1, rem lower minus equals 2, rem upper minus equals 2, sorry, minus equals 1, else cur plus equals upper. So is this every change that will happen? I hope so. Upper best, upper left, rem lower minus equals 1, rem upper minus equals 2. Seems about right. And then ans dot append cur. Okay, so this will do that. And once I'm out of that, then what I do is, so I figure out which one is lower. And that decides what I sort of swap with. I'll just write the code twice. So if rem lower is less than rem upper, so while rem lower, so what I do is I exhaust those, and eventually the idea is that, you know, I return, but while, so if rem lower is less than rem upper, then while rem lower is less than n, because I don't want to exceed n. So I have to keep track of what I'm removing. So while the elements that are in lower are less than n, because if they've exceeded n, okay, well, if it's less, and I keep doing that, eventually I might exceed and do that. Okay, so while rem lower is less than n, I can do the following. Cur minus equals lower left, sorry, minus lower list lower left, but I think before that I have to do lower left minus equals 1. So I subtract the score of this. Well, okay. So I need to add a new triangle. If well, the idea is, so I've used up everything, and now my remaining for lower is like 1, and my remaining for upper is like 6. So what I do is I increase my remaining for lower, but then I immediately use it up as well. So if my remaining lower was 0, then I have to free up 2 lower points, and then once I have 2 lower points, and if I have at least, okay, so I need to have 2 lower points. And why is that important? The reason, well, if I had even, oh yeah, what would happen if, so over here, if rem lower is greater than 1, then I can do this, otherwise I cannot do this, right? Similar thing here, upper best becomes 0 if rem upper is greater than 1, and do this. Cool. And then do this strategy. And so if something is only 1 left and the other is 2 left, then this will take that. So cool. So essentially what will end up happening now with this logic is I'm going to end up with 0 of one and k of another. And so what I need to do is each time I need to release two of the triangles that release one triangle that the lower was forming, and that will give me 2. So release 1, and then from the bottom I take 2, and then this process sort of repeats while remaining upper is greater than, okay, so while remaining upper is, I also have to make sure that I don't release more than this is possible. So while lower left is greater than 0 and rem upper is greater than 3, because I do need, it seems like I need 4 points each time. And then what I do is curve lower left minus equals 2. So I move this back, no, I move this back 1. Curve minus equals the lower list ka lower left, and then I add in 2. Curve plus equals upper list ka upper left plus equals 1, and then I do this again, and in the process the remaining of lower is the same, but remaining of upper gets reduced by 1, 2, it gets reduced by 2. So I just need remaining upper to be at least 1 or at least 2, because when I release this, that releases, no wait, when I release this, this only releases 1 point, so it needs to be at least, so it needs to be greater than or equals to 3, because if it's 3 points, and if then I remove the triangle formed by the lower, that gives me back 1 upper. Now I have 4 upper, I need 4 upper, so it needs to be at least 3 beforehand. Then remaining upper minus equals 3. Upper left is equals 1. This is fine. Yeah, okay, this seems like the right logic. Ans dot append cur after each happening, and then do it the other way around for that. Oops, yeah, but do it the other way around for this. While upper left, so I really wish that worked, multi-cursor. It's a way to do it, but I just can't, oops, yeah. And remaining of lower is greater than or equals to 3, then upper left minus equals 1. From the upper list I subtract, well, so I can just sort of do with this, right? So upper left minus equals 1, curve minus equals whatever this is, curve plus equals whatever this is, move this forward, do it again, and then remaining of lower minus equals to 3, and then do this, and then print len of ans, and then print star of ans. That's what logically makes sense to me. Hopefully there's not too many bugs. Might be some 2 with 2 and 2. Interesting. I'm not sure how that happened. We'll look into that. Negative 100, negative 50, 0 and 50. So 150 and 250. So there's clearly some indexing error or some other error. Let me just copy this and start debugging. Python debugger. So there's two things I need to do is check if the upper list is being generated properly. So, oh, is it because I'm doing... That's probably causing an issue. That should have been causing an issue, but I don't know if that was the only thing causing an issue. Does not look like it. It says something is out of range. Oh, no. So this is fine, it's just when I'm accessing the array I need to be smarter about it. So where am I accessing from lower list? I do it over here. So whatever this value is, so this needs to be greater than 1, this needs to be greater than 1. But even when so even if this is 1, no wait, sorry. It's supposed to be greater than 0, it's just that you do this before you subtract. Also you'd have to move upper left forward twice. Same with lower left. Think this might help. I'm not sure if it will solve it. So I'm still getting the wrong answers, but now I can maybe try and debug. Right, so lower list is 0 and upper list is... So the input was 0, 1, 0, minus 1. Lower list I get, yeah, that would be 2, that's fine. You go through this. Lower best is 0. What am I doing here? Oh yeah, I'm initializing the value in case. And then this stays 0. Wait, why did I even go over this? Rem lower is not... So this is wrong. Okay, let me run that again. Create. And skips that. Cool. Should go in here. Should set that to 2. Add that in. Cool. Remaining upper is 1, yeah, because that is left, but there shouldn't be anything that you can do. Yep, great, that is good. Okay, so the input was 0, 100 and negative 100, negative 50, 0, 50. So the first move, lower list is, yeah, you can get a 100, and upper list it should be negative 100 to 50, which is 150, and negative 50 to 0, which is, yeah, 200. Oh, well, that's an issue because I'm storing it like this. Let me see if it is in fact an issue. It should be. Right, so this will exhaust. Will it exhaust? Mm-hmm. So it took the 150 length one, and now it's going to take the 50 length one. So okay, this is fine. That's cool, but I do think I don't need this anymore, which means I also don't need to set this to initialize as 0. So this should just be the benefit of that array and the benefit of this array, and then I no longer have to do the jugaad I was doing here with the plus ones and the reorderings. So hopefully it should now work for the other test cases as well. Should I run it directly? I kind of want to. So this should give me 1200. Yep. This should give me 499, 198, 260, 283, and this should give me the wild numbers. Yes, this works. Logically, it should be working. I do want to check it for the last test case, just in case I can catch anything, but I don't think I will be able to. Right, it's lower list and upper list, and they carry these numbers, which are cool and handy. And the idea is you add whatever you think is best, but now you're kind of out of items, so then you sort of backtrack and fix that, and then you're out of items again because this still does need some lower triangles. Okay, cool. Seems legit. No idea. Maybe I'm just a bit tired as well. Let's go. Okay, that was a lot of effort. Okay, I hope this was useful. I do realize most of this is just me going insane and it's very hard to follow along, but I wanted it to be as raw and as true to how I do it as possible. The only difference is I don't typically use this. I just do things on my tablet or on a piece of paper. It's easier to work with, but I think most of what I've done here is what I would have done on pen and paper anyways. It's just that this is uglier. And when I was doing the test cases, I could not do it on this because that was too much effort. But yeah, that is how I solve problems. I would do E, but not while recording. That is too much effort.